Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept of maximum suction lift or suction height for a centrifugal pump. So this is for centrifugal pump. So the diagram what I have taken here, this is the diagram of a pump of centrifugal. So this is the pump, centrifugal pump actually, and we need to find out the suction height. We need to find out the suction height. So in this diagram, we can see this is our free surface of the liquid. So at this free surface, we have a atmospheric pressure. This is P atmospheric, we can write. And this is our sump level. This is our sump level. This is our sump, or we can say that is a reservoir. This is a reservoir of fluid. And in the bottom of this, we have a foot valve. This is our actually foot valve. So these are the parts or equipments which is involved in the centrifugal pump. So this is the pump and this is the casing. This one we can consider this is a runner. So in the runner we have number of blades are connected. So these are the blades, and this is our suction pipe. This one is a suction pipe and this is our delivery pipe. So this is the delivery pipe, and here this is delivery valve we can consider. Okay, so these are the points which are involved in this pump. So to identify the suction height, what should be the suction height? Should be the maximum suction lift. Okay, so first we will consider the suction pipe. We won't consider, we won't discuss about the delivery part here. So in the suction part, if you see, as I told you, this is the runner part is there. So the water will be lifted from the sump level through this suction pipe, and here it is Vs and this is Hs. So Vs is the what? This is the suction, what is the vacuum is, or what is the pressure at the suction pressure is there. Okay, so at this point we can see what is the Vs value and what is the Hs. Hs is nothing but this is the height. This is the height of suction, and this is actually eye of the runner. Okay, eye of the runner or impeller actually. Runner we used to call for the turbine case. Here we used to call this is a impeller, and this is eye of the impeller, and inside this we have a shaft which will be connected to the motor. Now here let's consider, as I told you that we need to find out the suction height. So the suction height means what is the height of lifting here, how much distance should be there to avoid the cavitation. So this is our base level. If see, this is the base level and this is the maximum height. So this is one level and this is another one level. So these two levels can be defined. One is, suppose we can give this is section 1 and this is section 2, or we can give, though this is working here at P atmosphere pressure, I'll just mention here A. Okay, you can take section AA, or you can just keep 1 and 2. You can give anything. So to find out the suction height, okay, how much height should be required minimum, we need to apply the Bernoulli's equation. I hope you remember the Bernoulli's equation. If you have forgot this one, you can see our previous video lecture where we have discussed the Bernoulli's equation between two different sections. So by applying the Bernoulli's equation, at which point one is apply Bernoulli's equation at free surface of the liquid, free surface of liquid and the sump, and at section 1 which is the suction pipe, and inlet, just inlet to the impeller. Okay, inlet to the pump, you can say at inlet to the pump. Between these two, let apply the Bernoulli's equation. Now we know that the Bernoulli's equation is all this energy, the total energy at one portion equal to the total energy at the other portions. So let me write here what is the value here, P by rho g. So here PA, I can write the pressure at this atmospheric, what is the value is there, by rho g, plus V square plus VA square. So V square in the sense VA square, right? VA square by 2g plus Z1. Z1 is nothing but ZA. This is the Bernoulli's equation at this label. Similarly, the Bernoulli's equation at this point, what? Same thing I can write here, just I'll change the note here, P1 by rho g plus, here it is, you can write V1 square by 2g plus Z1 plus Z1. Now along with this equation, though the fluid is flowing through a pipe, there is some losses will be there. So I'll just mention some losses, HL. Okay, so these things, P by rho g, already we know that, if you remember, we know that P equal to rho g h, and here to find out the head value, we know that we need to find out P by rho g. That's why it is called pressure head. Okay, that's why it is called pressure head. This is velocity head, this is potential head. Okay, so from that equation we got. Now here, what are the terms are there? What are the terms are involved? Just I'll tell you. PA. PA is what? That is atmospheric pressure on the free surface of the liquid. PA. Second one is, these are the terminology are involved here. Now rho is the density of the liquid, and g is the gravity value, and next VA. VA is the what? Velocity of the liquid at the free surface of the liquid at this point. So VA, actually the value of the VA will be 0 because there is no fluid is flowing at this point. Okay, after that the fluid is flowing, suppose. So there is no velocity here. So the VA at this point will be 0, starting point. And the next one is, this is ZA. ZA is what? ZA means at this datum surface or at the free surface. What is the value? How much head is there? That is the starting point. So there is no value of distance. That is Z equal to 0. So that is the height. And next one is second part. That means at the section 2, we have the value like P1. So similarly, P1 is nothing but the pressure of the liquid at the before going to the inlet of the pump. So that one we can consider the absolute pressure here. And next one, similarly V1. V1 is the velocity of the liquid through the suction pipe. So this is the velocity. Okay. So how much is there? So the V1 we can write Vs also. This is the suction velocity at this point. And the next one, Z1. Z1 equal to what? Z1 equal to, we can write how much height is there, the total distance from here to here. That is Z1. Height of the inlet of the pump from the datum line. So this one also you can write, this is our suction head. So these or suction height, these things we need to calculate. Here it is mentioned how much height is there, HS. So this one we need to find out. Now in this equation, just to put these values like PA by rho g, we will have a value of PA by rho g. This is the V1 square. This is V is 0 here. So let me keep 0 plus Z equal to 0. No distance is there. In the right hand side, we can write here, this is P1 by rho g, plus VA square by 2g, and plus here in the place of ZS, let Z1, I'll write HS, because that is the height. You can see this is the suction height, how much height is required, that is our target to find out. Along with that, the HL. So HL is what? HL is the, here one more is there, HL, that is the head loss, the loss of head at the football. Here you see the loss of head at the football, and this is football and strainer, both are there at the suction pipe. So this HL also we can write HFS, that also we can write here. So here also I can just mention on behalf of HL, I can write HFS, football and strainer. Football and strainer both are present here. Okay, so some losses will be there from this point to, like when the liquid will be flows between this, so there is some losses will be there. So that one we can write in this way. Now, so final we can write this like P, let me keep it one side, P1 by rho g, P1 by rho g, this one, and the other terminology I'll take it to the other side, like this terminology I'll take it to other side. So we can write here, this is PA by rho g, and this one minus of, this is our Vs square by 2g, and this is plus HS, and we can write this is HFS. Okay, and some books it will be given, like we can write HS. Okay, HS will be like, we can keep here HS, and the other side we can write, this is suppose the total whole minus I have taken, if I'll take to other side, so here HS I can write, this is HA. That means HA is the same nothing but, if I write here HA, that is nothing but PA by rho G, this one, PA by rho G. So HA minus, I can write this is suppose P1 by rho G, P1 by rho G minus this is V1 square by 2G, V1 square by 2G or VA square by 2G, and minus HF, or we can write HFS or HL. So some books will be given like this. Okay, both are correct. There is nothing wrong in this. Now this is the equation. What is, okay, let me give equation number 2, and this one we can give equation number 1. Now what is the requirement for us? To find the maximum suction lift. Okay, to find the maximum suction lift. To find the maximum suction lift, the pressure should be, the pressure at the inlet of the pump, it should not be less than the atmospheric pressure or vapor pressure of the liquid, not atmospheric pressure. This pressure should not be less than the vapor pressure of the liquid. So vapor pressure is what? Vapor pressure is, we used to mark it like PV. Okay, this is our vapor pressure. So the pressure which is present in the liquid at this inlet point, that should not be less than the vapor pressure of the liquid. So to find out this maximum suction lift, okay, the pressure at the inlet of the pump. So what is the pressure at the inlet of the pump at this point? Because here this is the inlet of the pump. Okay, so that should be equal to the vapor pressure of the liquid. So what I can write here, I can write P1 equal to PV, which is the P1 here. This one I have taken P1 at this point. This one P1. So that should be equal to the vapor pressure of the liquid at the inlet of the pump. But this both should be equal. Now, so what I'll write here on behalf of PV, I can write P1. Sorry, on behalf of P1 I can write PV. So here I can write PV by rho G, and this is equal to, we can write PA by rho G, correct? This is PA by rho G, and this part will be minus. Here it is, we can write Vs square by 2G and plus Hs and plus HFS. This is our normal equation what is there. Now again what I'll do, I'll keep the PA by rho G one side. So here what I have written here, similarly I will write just one side, PA by rho G. PA by rho G equal to what I can write? Now PV by rho G minus, this minus was there, if I take it to other side, that will be total whole plus will be there. So we can write this is Vs square by 2G plus Hs plus HFS. Okay, now this is our what? This term is already I told you here. This term is our, that is our atmospheric pressure head. So this atmospheric pressure head also we can mark it HA. Okay, so that is in meters actually. So, and similarly this is like, let me write here, HA is the atmospheric pressure head. Atmospheric, this is our atmospheric pressure head, which already I have mentioned here. That one we can write, this is PA by rho G. Okay, and similarly we can write the next one, HP, the HP. So HP is equal to what? HP equal to similarly vapor pressure head. This is our vapor pressure head, and this vapor pressure head we can write in the term of like PV by rho G. So that is PV by rho G. So either you can give the small h or you can give some capital H also. Even sometimes it will be given like HA like this, and this will be given HP. So here I'll just put the value of these things. So I can write here what I'll write. Let me consider the capital HA suppose. Now this is HA and this equal to HB plus what is there? Vs square by 2G, and this is plus Hs and HFS. So finally what is our requirement? What is our requirement? I told you that we need to find out this height, suction height. That is our main motto. Okay. So this maximum suction height Hs, I'll keep it in the left hand side. If I'll keep this one at the left hand side, what will get in the right hand side? So that is nothing but HA minus, this is HV, and this is minus VS square by 2G. Okay, and this minus HFS. This minus HFS. So this is the our final equation. So this equation we can mark it equation number 3. So this equation 3, actually this will give us the value of maximum suction lift. What I told you in the starting, we need to find out the maximum suction lift. Okay, so for the centrifugal pump, this is the maximum we can write suction lift for centrifugal pump. Okay, and so that the suction height should be any pump. Okay, should for suction height of the pump should not be more than this value. The value what we'll get, okay, suppose we will get some value of like suppose 0.8 meter. Okay, or suppose 10 meter is there. Let me tell you, suppose some value is there. This is the value. So the suction height, this suction height of any kind of pump based on this value, it should not be more than this value what we got by this one. Okay, if the suction height, okay, if the suction height of this any kind of pump, okay, it will be more than the vaporization of the liquid at this point. The vaporization of the liquid will be takes place at this point. If evaporation will be takes place means obviously we know that cavitation occurs. So to avoid the cavitation, we have done these many things are there. Okay, to know the cavitation value, how to see, once you identify that what is the maximum height should be there, that the pump should be placed, then we can easily do this process and we can avoid the cavitation. So to do this, like why this required P1 equal to PV we need to consider? Now to avoid cavitation. And why we are calculating this one? Again same thing, to avoid the cavitations. Okay, so the process is what is done, that is all the things we have done for the to avoid the cavitations in the centrifugal pump. So I hope you understand. If you are having any doubt and query regarding this theory, you can give us some comment in the comment box. Thank you all.